All right, guys, so before we get started, are there any questions on the homework or anything we've done so far? And for today's lesson that we're going to be looking at, it's not going to be any real different than what we've been doing so far. A lot of, well, when I say that, I mean stuff that we've already done before that's not, overly brand new. It's more probably kind of a refresher of stuff we've done. I think the only one of the sections that we've covered so far that's been really kind of overly challenging probably was, I think, P3 when we talked about solving equations, solving those functions. That was one of the harder ones of the group. Now, what we're looking at today is kind of the vertical line test, finding zeros, determining intervals where the function's increasing, decreasing, determining relative minimum, relative maximum, and kind of these different parts of a function of its graph. Now, out of all of these here, there's only going to be, I think, one main one that's going to be new. So highlighter. And it's identifying even and odd functions. I think this is going to be the main thing that's going to be new that you haven't really delved into, except for, well, yeah, I think they delved into that last year, yes. And it can be kind of confusing at first, especially if you aren't really sure what you're looking at or what you're trying to figure out. So that's going to be the main new thing, the graph of a function. And really we're saying that for any algebraic point of view, it's the graph function is the collection of ordered pairs. It's the collection of points connecting the domain and range, the x and y value. That's all a graph is, and it helps us to visually see what the function looks like. X is equal the directed distance from the y-axis. Y equals f of x equals the directed distance from the x-axis, our x and y values, input, output. And when we talk about the domain, we're talking about the x values. So when we look at this function here, well, the domain is all the x values from -1 to 5. We would include -1, but we wouldn't include 5 because of the open circle. It's a hole. And the range is going to be all the values from, see here, so it'd be 3 to -3. Those would be all the range values going up and down. And we talk about the function f of -1. So at -1, where x is -1, we look for the y value, which is 1. And at f of 2, the y value is -3. We're just looking at those points. Questions on this here? So the closed dot at -1, 1 indicates that x is equal to -1 is in the domain, where 5 is not. So the interval would be bracket -1 comma 5 parentheses. It's on that interval. And we kind of walked through this already. Open and close at the extremes beyond the point. By definition, none of this is new. Vertical line test, a set of points in a coordinate plane is the graph of y as a function. So if we can draw a vertical line and it crosses the graph at any 2 points, it's not going to be a function. I'm not even going to really bother with this too much because zeros of a function. We're just trying to find out what value of x will make the function equal 0. When we solve a function or solve for an equation, we're trying to find out what value of x will make the function equal 0. We've done this time and time again. And really, when they talk about this here, we're just trying to see where it crosses the x-axis. It's x-intercepts. So we could graph it and see where it crosses. And that really would be solving it. And it talks about it especially in the homework. Well, let's solve it algebraically and graphically. So write it out as we did in P.3 to find the zeros. And then we graph it to see if those points match up to what we found. I don't think that's anything new or anything crazy that we haven't already done. Because we could go on and graph these here. Apparently I'm just going to... Okay, there it is. Unlock. I'll delete it. Because for the first one, we could go through and solve the quadratic and see, okay, it has zeros at 5/3 and -2. Nothing that we haven't already done. And if we graphed it, it crosses the x-axis at 5/3 and -2, where we expected to find the zeros because that's what we found algebraically. We'll also see it graphically. For this one here, the square root of 10 minus x squared. Well, we can square both sides, add the x squared, take the square root, and find out it's plus or minus the square root of 10. And again, we can see that graphically here. Now, do y'all know why, or do you know how to approximate a square root if we don't know the exact value? Well, this is somewhat handy. I mean, out of all the stuff we'll cover, say the square root of 80. You know, on a number line, where would that be close to? What would the square root of 80 be close to? Anybody have a guess? Right, we could, yeah, it's really close to 9. Because I think for those of you who've had me, because 2 of y'all haven't, especially in Algebra 2 and Geometry where we dealt with square roots, and you'd see me throw out a number of what it approximately could be, there's actually a method behind it. Because if we think about 80, what is the next perfect square? 81, yes? What's square root of 81? So this here should be close to 9. It's 1 away, so it should be really close to 9. So we're looking at probably 8.9. So Aiden, what did it give you? Yeah, you're good. 8.944271. Yeah. So we can approximate that way. So if we look, say, the square root of 10 on the last one, well, what's the closest perfect square to it? 9, yes? And 9 is 3. Square root of 9 is 3. So we're looking at a number that's just barely past 3. And if we look back at the graph, because 3 would be about right here and right here, so we get an idea of what the number is. Does that kind of make sense? So we can do that there. Now, actually getting close to those numbers is not nice. It's not easy if you're doing it by hand. Because if you're doing this by hand, okay, we can say 9 is close to it. It's going to be too big. So then we would do 8.5 times 8.5. Okay, that's too small. We can do 8.7 times 8.7 and just work our way slowly to it. I'm not going to bore you all with that process, but I thought that's a little interesting thing for y'all to see so we can start figuring out what they are. Yeah. And we get this here. Increasing and decreasing. We'll look at this next. So you may know about graphs of function and the function itself. So the more you know about the function itself. So the more we know about the graph, the more that we know about the function itself. So if we look at this here, it's increasing, decreasing, and constant. Well, it says, as we're coming from left to right, that this portion of the graph is decreasing, this portion is constant, and this portion is increasing. One's going down, one is staying the same, and one's going up. And we always read it from left to right. And we talk about the increasing or decreasing on the interval of the x-axis. So we talk about the x values for which it is increasing, decreasing, or remaining constant. Now we do have a definition for it. And it's this here. So a function f is increasing on an interval when for any x1 and x2 in the interval, this statement's true. x1 is less than x2 implies that f of x1 is less than f of x2. And again, if that's not completely clear, that's fine. All we're saying is that I have two x values. One's bigger than the other. So if we're looking at a graph, well, I have this x1 value, which is less than this x2 value. We're talking about we're increasing on the x-axis. And f of x1, this point here, well, is going to be less than the f of x2, the y value. So it should be going up. That's all it's saying, is that the x value that we start with is less than the other one. It's moved farther right, and the y values went up. That's all we're talking about for increasing. Decreasing. Almost the opposite. Essentially, we're saying, again, we're still moving along the x-axis to the right. But this time, the first y value is bigger than the second. So it's decreasing along the y. Still increasing along the x, but decreasing along the y. And the last one, the y values are the same. We got it straight. Questions on any of those here? Not too bad. Especially if we're looking at a graph, it's kind of easy to see what's decreasing and what's increasing. And what they call these points, where it, especially where it changes from increasing to decreasing, is what they call a turning point. Again, it kind of makes sense because it's turning from increasing to decreasing. To go from one to the other, it's got to turn. So if we look at these graphs here, because if we look at A, this one here, even though here at the center it does look like it's starting to decrease, it's actually continuing to increase. Because for any of those points, it's still the y values are getting bigger. So for this one here, it's actually increasing on the interval of negative infinity to infinity. Just the normal cubic function is just going to increase the whole way across. Now, I'm going to pull up the graphing calculator so that we can not so much graph this function, but look at the table of values so that we can see this here. Y equals clear x to the third. Because as we look at these y values coming down this way, they are all increasing, because negative 729 to negative 216 to negative 64 to negative 8 to negative 1 to 0. Those are all still increasing. They're increasing at a slower rate, but they're still increasing when they hit 0 and then go 1, 8, 27, 64, and then they take back off. So for all of these y values, the amount that they're increasing is still increasing. It's just increasing at a slower rate. So it's kind of tricky, at least for the cubic function, our basic cubic function, because there at the center it looks like it could be decreasing. But the values are still increasing, it's just not at a fast amount as it was at the beginning or towards the end. Now for the second one, there are definitely increasing and decreasing points. Yes? Because if we look at it from left to right, well, we start off with increasing. Because from negative infinity, where's our x value where it stops increasing? At negative 1. Because at the negative 1, 2 is where it stops. We don't care so much about the 2, the y value, we care about the x. Because we're going to strive this along the x. So from negative infinity to negative 1, it's increasing. And then it decreases from negative 1 to 1. Because from negative 1 to 1, it's going down. But at negative 1, or not negative 1, at 1, it starts increasing and goes off the map. So it's increasing from 1 to infinity. So we're just describing it along the x-axis. And yes, we're always going to use parentheses on these here. Because we'll always use parentheses with increasing and decreasing, because at these points that we call the turning points, it's technically not increasing or decreasing because it's turning from that spot. Any questions on this here? And for the last one here, well, we are increasing. Yep. Might be helpful to create a little bit of space. Here, right? is we start off increasing from negative infinity to what x value? 0. What happens at 0? Yep, it's constant from 0 to 2, and then we start decreasing from 2 to infinity. And that's it. He's not too bad. And really that's increasing and decreasing. However, however you can use calculus to determine for certain all intervals on which a function is increasing, decreasing, or constant. And it's really taking the determinant of it, trying to find its value and seeing how it works. Or it's really taking the slope, repeated slopes of a line coming around. Now we also have something called relative minimum and relative maximum. And I definitely talked about this in Algebra 2. Because when we talk about some functions, let me go back for this here, because it's sometimes good to see graphically what this looks like. Because if we look at these here, so we're going to look at this one. Now, we know that this is going to continue up and down, yes? Is there an actual maximum or minimum point that we have? Is there going to be an actual biggest point or smallest point? Well, no, because this continues up, no matter what point I pick, there's always going to be one bigger than it, no matter what I do. The same thing is true going in this way here. There's always going to be a point smaller than whatever point I pick. So we talk about a relative minimum and relative maximum. There's a relative, so within a certain range, these two here would be a relative minimum and relative maximum within their confined range. So we can have multiple relative minimums or maximums for these here. Now a quadratic, our U-shaped function, does have an actual minimum or maximum because there is a highest or lowest point. But a lot of our odd functions don't have those. So we have different places that we can see them. And here it's just saying over this constrained space, between two x values on either side of that point, one is increasing or decreasing. This is the smallest point for that range. And the same thing is true for maximum. This is the biggest point for this set interval of values. So they gave us a picture. So these points down here are the relative minimum for their set area or set constraints. They are the smallest point in that range. And the same thing is true for these here. Over these set intervals, these are the biggest points for that set one. And that's really it for relative minimum, relative maximum. They'll sometimes call them local minimums and local maximums because they're locally in that area. And that's it. So increasing, decreasing. Average rate of change, just finding essentially slope over those certain periods of time. Any questions on this so far? Odd and even functions. This is the one that's a little bit different that most likely you haven't dealt with before. You've dealt with odd functions, you've dealt with even functions. And in most cases, because I brought this up some, we can kind of tell what one is, or we talk about quadratics as being even, or most quadratics are even functions, and most cubic functions are odd functions because they have one or the other. And this comes up also with sine and cosine as even and odd. Because sine is considered odd and cosine is considered even type functions because of how they work and how they operate. And there's different things beyond functions that even and odd functions work with. There's for most of y'all, Rubik's Cubes are something that y'all know of with, and they're kind of interesting for the most part because we can describe these by mathematics for how they function and work in matrices and talk about rotations and turns and their permutations actually through mathematics itself. Now, for the most part, there's not too much interesting with these in that no matter how it's arranged or the permutations that you do to it, mix it up, there's always a way to get back to the start, no matter what you do to it. Now, I have another one here, and they call this square one. And the reason that this one's different is that this one actually can be set up as an even or odd function. And if you're not dealing with what they call its cubed form, so keeping it as a cube, because for those of you who haven't messed with this or looked at this at all, it's very easy not to get it into a cube. And make sure set up just right. All the center pieces are actually right next to each other. We have this here. So this is definitely not a cube anymore. So you can get it out of cube form, but there are ways to solve it keeping it as a cube. But the big issue, and turning it just like that, is taking it out of even and now it's odd. Which means that there's no possible way to solve this and keep it as a cube because it's now odd. And it mainly comes back into the end when we're solving that the last set of moves are finishing up the edges. Yeah, luckily or unluckily, it's been a while since I've done most of this here. So all the moves, try to keep it, except this is the only one that I do out of it. Keep it in this form here, keep it as a cube. And we can do most of them here, and it's back into a cube. Luckily. I messed with this the other day, and otherwise I'd be trying to remember one of the last moves. There we go. So those two, so those two. Do there. There we go. Because the first thing I'm trying to do is just get the white on top, white on bottom. And then we can rearrange the sides, which luckily for me, only the bottom was out of sorts. Okay. Didn't do what I want. I can flip the sides, so kind of rotating these two. And I know this is probably not the most interesting thing in the world. Okay. And the last thing that really doing in solving this, once I get the sides, and I'll show you this here. There we go. Green, we're all together, red, corners together, blue, orange. Now it's just the center pieces are out of place. And what comes involved here is that we can switch two at a time. The only way we can permutate is these two and these two. We can switch those. So if I want to, I could switch orange and red here. And then we can look at the bottom and try to switch it so that it works out better, because I can switch these two. And doing this move here will switch it. Now the orange set up nicely. I've got red here. So down here I can switch the orange and red on this side, and then up top we can switch the green and blue. Orange together, blues together. So I need to switch these two, and it'll be solved on top. And on bottom I can switch these two to get closer. So if we look at the top is completely solved, which is nice. And if we look at the bottom, well, these two are out of place, yes? But the rest of it's fine. So I can put these here to switch these two. If we do this, okay, we can say that the bottom layer is completely solved now, yes? And the top now has two flipped, yes? This is what they consider for this here to be odd, because I have to have two here and two here. So no matter what I do, keeping it in cube form, it will never be solved. I can't solve it because it's considered as an odd function. So we'd have to go and change it back from odd to even to actually finish this up and solve it. So that's one of the reasons this one here is a little more mathematically interesting than a normal 3 by 3. Because in a normal 3 by 3, no matter how it's arranged, it's solvable as a cube. This one here is not. I have to actually take it out of cube to get it there. So that's kind of an interesting thing with, well, I think is an interesting thing with this here. And I intentionally, because I came across that in the abstract algebra class that I took in college, I intentionally retook that class to be able to do that project. The professor I took it with the first time did not do that project. And we actually had to solve it in front of the professor as part of our grade. So, but I thought that'd be a little bit interesting beyond the boring stuff we've been doing today to talk about these even and odd functions. Now, when looking at even and odd, this here is the main thing. This is the main part. Because when we talk about a quadratic, it's an even function. So x squared. If we multiply a negative by itself, it becomes positive. So what we're saying is that f of negative x, if I plug a negative x in place of x everywhere in the function, and it simplifies back to the original function, it's even. It's an even function. If f of negative x, I plug that negative in, and it's the same as if I applied a negative to the entire function, then it's odd. So, now we're saying that this function here is odd because of this here. Well, being told something and actually seeing it are two different things. So what we're saying is that I'm going to take g of negative x. Well, g of negative x, I'm plugging negative x for every x. So that means instead of having x cubed, we have negative x cubed minus negative x. We just replace the two x's with negative x. Now, for us, negative x cubed, well, a negative times a negative times a negative multiplied by itself 3 times is still negative. So we'll still have a negative. And this would be x to the third. Here, we have minus x. Well, negative and negative make a positive. So g of negative x is the function negative x cubed plus x. We good with that there. Now, what we're saying, for this to be odd, it needs to be the exact same as negative g of x. Negative g of x. Well, our g of x function is x cubed minus x. So we're going to distribute that negative through this time. Well, negative times x cubed is just going to be negative x cubed. Negative times negative x is going to be plus x. And this is our negative g of x. Are these two the same? Yeah, so this here would be considered an odd function. So really all we did was see what g of negative x was and negative g of x is. And if they're the same, it's considered to be an odd function. And that's it. Now when I do these here, I always check to see if it's even first. Because by definition, even is saying f of negative x, when we plug the negative x in for x, does it match up to f of x, our original function? So for this here, okay, I found net g of negative x. Well, are these two the same? Well, no, so it's not even. Then we can apply the negative to the outside to see if it's odd. And then that's it. Now this one here, again, it already told us it's even. But the way that we see that is taking h of negative x. We're plugging in a negative x wherever x shows up. So for this here, we can say negative x squared plus 1. Well, negative x squared, negative x times negative x is just going to be x squared plus 1. Well, is this the same as our original function? Yeah, so it's even. And that's it. That's really all we're doing. We're plugging in negative x first into all the spots and simplifying and seeing does it match up to the original function. If it does, then it's even. If it doesn't, then we check negative of that function. We apply the negative through and see if that matches the negative x plugging in. So we're starting off with, so here, h of negative x, is that the same as h of x? If yes, it's even. If not, we can see, does it equal negative h of x? And if it does, then it is odd. And as much as we'd like to think that it's going to be one or the other, there's always the third option of neither, because there are a good number of functions that aren't even or odd. They're neither. That's it.